So in the next example, we'll do a Maclaurin polynomial for e to the x. So in general, just like for general value n, right? So for some arbitrary n. So what we're really looking for is just p sub n. So if we kind of go back to what a Maclaurin polynomial is, so we have the series definition, and we have also the nth degree polynomial. So again, an nth degree polynomial is going to be terminated at x to the n with the nth derivative of f. A Maclaurin series would be infinite. But I can write both using summation notation. So just in general, this is going to be starting with 0. Maybe I'll use a different n just for clarification. So for some fixed n, so you always want to take the derivative, and because it's Maclaurin, we know that we're evaluating at 0. We have x to the power matching the index over n factorial. And so for us, we know that every derivative of f of x is just back to f of x, right? Because we know f of x is e to the x, and f prime of x is e to the x. For every single derivative of any order, we're always going to be e to the x. So therefore, we know that f to the n, as far as derivatives are concerned, evaluated at 0, equals 1 for any value n. So that means that I can write because I know that the nth derivative evaluated at 0 for any value n is equal to 1, I can just say that this is 1 times x to the n over n factorial. Moreover, I could just omit that 1 in general and say this is n equals 0 to some arbitrary capital N of x to the little n over n factorial. And so that would just look like at 0, it's just going to be 1, and then it's x, and then it's x squared over 2 factorial plus x cubed over 3 factorial plus so on and so forth, all the way up to some kind of general stopping point n, right? So I could have said for, give me the 5th degree polynomial for Maclaurin polynomial for f of x, and so we would know that this capital N is 5. All right, so here's an example where we're not going to center at 0. So this is a true Taylor polynomial, and we're going to center at x equals 1. So the first thing we need to kind of organize is just what each polynomial is going to look like. So we know that P0 is just the 0th derivative, which is just the function itself, and we're evaluating it at 1. And then we also have to take x minus 1 to the 0. So if I really were to write out every single thing that goes into this, that's really what it looks like. However, the 0th derivative is just f of 1, like we said, and x minus 1 to the 0th power is just 1, and 0 factorial is just 1. So P naught or P0 is just the function given, ln of x, evaluated at the value 1. Then for P1, we're going to add another term. So we know that we're at f of 1, and now we have to add the first derivative, f prime, evaluated at 1, and then x minus 1 to the first power. over 1 factorial. And again, you can simplify this a little bit because it's just f1 plus f prime evaluated at 1 times x minus 1. So this is really kind of what we did in the first examples of this lesson. For the second degree Taylor polynomial approximation for ln of x, it's the stuff we had before, so f of 1 plus f prime evaluated at 1 times x minus 1. And now we need to go ahead and add the second derivative. So this is the second derivative evaluated at 1 times x minus 1, that's the centering bit, square that over 2 factorial. And P3 will be similar. So this is just the old stuff from P2, and then after I finish this, we'll append the third degree term. So that's going to be the third derivative evaluated at 1, center it at 1, cube it over 3 factorial. And then the last guy is P4. So again, all the same stuff as before. And then for the fourth degree, for the fourth derivative, I'm just going to write f and then in parentheses 4, because I think after 3 apostrophes it gets a little funky. So it doesn't mean raise it to the 4th power. It means take the 4th derivative, evaluate it at 1, multiply that by x minus 1 to the 4th power, and divide by 4 factorial. So each time we add another term to our Taylor polynomial, the approximation to the original function gets better and better. All right, so let's go ahead and crunch them out. We need to know all of our derivatives and what they are at 1. So I'm going to make a little table over here on the right hand side. So I'm going to have f of x. I need the first derivative, I need the second derivative, I need the third derivative, and the fourth. And then what I need to do is I also need to evaluate it at x equals 0. So x equals 1, that's where we are. So without taking the derivative, I just have the original function, right? ln of x. So ln of 1 is 0. And then the first derivative of the natural log is 1 over x. Evaluate that at 1, we get 1. The second derivative is negative 1 over x squared. Evaluate that at 1, we get negative 1. Third derivative is 2 over x cubed. Evaluated at 1, we get 2. And then we get negative 6 over x to the 4th. If we evaluate that at 1, we'll get negative 6. So now what happens is we can go back and plug all these values in and get the approximations that we need. So here we have all of the values that we needed to compute on the right hand side. So I'm kind of just going to plug and chug here. So we're going to get, let's see, for this first one, we're just going to get that P0 equals 0. Then P1 equals 0 plus, so we need the first derivative, which was 1. So I'm not going to bother writing that, x minus 1. So this just equals x minus 1. And then for the second degree Taylor approximation, we'll bring down the old guy, x minus 1. And now let's do the second derivative. So the second derivative was negative 1. So this is going to be minus 1/2 x minus 1 squared, right? So that 2 factorial is just 2. And then for P3, I'm going to take everything I have before since I don't want to keep computing it each time. So I know that this is my 0th, first, and second term. So now I'm going to add the third degree term. So the third degree was 2. So that's going to be 2 over 3 factorial, which is 2 over 6, which is a third, times x minus 1 cubed. And then for the last piece, we have to do all the same stuff, 0, 1, 2, and degree 3 terms as above. And the last thing we're going to put on the end is the fourth degree term. So the fourth derivative evaluated at 1 was -6. -6 over 4 factorial is -1/4. And then I still have x minus 1 to the 4th. So these are all our various degrees of Taylor approximations centered at x equals 1 for the given function natural log of x.